Okay. So, yes, what is your very general question?
So for like 21 and 32, which were pretty much based with the harmonic series,
Mm-hmm.
like the divergent, could your explanation just be because it is a multiple of the harmonic series, both it's divergent?
Yeah.
I'm kind of confused on how to explain it.
Yeah. Because when you're looking at 21, you can actually take that constant multiple out using rules that are based in sigma. And then you have the harmonic series is divergent, and multiplying by a constant has no effect on diverge. And then with this one, if you have a sum, you need for the two things that you are adding to be able to both converge. Now, there are some little issues of things canceling each other out that I'm not even getting into right now. And those are more complicated situations. But with this one, you can break them apart and see a converging geometric series. But if you add a converging geometric series to a diverging harmonic series, there's nothing you can do to make this thing converge. And you can take this, and again, you can factor out the constant multiple and then just claim it as a harmonic series.
Okay, awesome. Thank you.
Uh-huh. And I'm going to go step by step with number 3, and I might even do 4 as well. Those were the problems that were more asked for in the last period that I did. So here is the key to the, suddenly my words left me. The ratio test, there we go. I'm highlighting all of the ends. Now, this is a more extreme case. Normally, you're not going to have this many ends to deal with, but if you can do the extreme case, you can do anything. When you do the ratio test, its limit is n approaches infinity of the absolute value, and it's the n plus 1th term over the nth term. We save our pain of fraction within fraction by first writing the fraction of the n plus 1th term and then reciprocating the formula itself, because this is the a sub n itself. So I'm going to now start the ratio test. Limit as n approaches infinity, absolute value. And I have negative 2 to the power of, and I just realized I need to erase that. It's going to get in the way. And it's 1 plus 3 times, and I substitute into the n in n plus 1. And then I have n plus 1 plus 1 quantity n plus 1 squared, and 5 to the 1 plus n plus 1. I'm just going to write n plus 2. And someone's got their mic on. Someone's got their mic on. Let me see if I can mute. Oh, there we go. No. Okay. I'm not sure if that was my muting or. Okay, here we go. So I've plugged in the n plus 1. Then I'm going to multiply by the reciprocal. And yeah, these are these are problems only during COVID that we can laugh at someday in the future. We will fully laugh at all of this. believe. Anyway, so now all I'm doing is I'm reciprocating the formula that I see. And where did I go? There it was. And so that's the initial setup for the ratio test. Now, I want to realize what I can actually simplify. If I have a same base and I'm dealing with multiplication division, I can use exponent rules. Now, this exponent that I just highlighted, I'm going to write it is 1 plus 3n plus 3. In other words, 3n plus 4. And then the other exponent needs to subtract from that, but I need to make sure that I'm subtracting with a parentheses. So I'm using my exponent rules of same base, subtract the exponents. And that gives me 3n minus 3n, bye-bye, and then 4 minus 1 to give me 3. So when I simplify what is in here, I have negative 2 to the third power left over between those two pieces. The other piece that I can simplify, I have another base that is in common, 5. I can also subtract its exponents. A little bit faster would be to realize that I have one more 5 in the denominator than I have in the numerator. So I have an extra divided by 5. And then other than that, what is in yellow and blue is gone and simplified. The things that look like polynomials, I can't actually simplify. The limit will have to take care of them. And I'm just going to write to the side. Oh dear, I'm running into other stuff. Okay, I want to not mix stuff, so I'm going to rewrite down here where I am at of negative 2 to the third over 5. And now I'm going to write all the n stuff. I have an n plus 2 times an n squared, an n plus 1 squared, and another n plus 1. And what you want to see in all of this is you have a third degree polynomial in the numerator and a third degree polynomial in the denominator. The leading coefficients are 1. That entire piece by itself is heading to 1 and then multiplying by this number over here. When I take the absolute value of it, I get 2 to the third power over 5. And so I have an answer to this limit. When I'm using the ratio test, I have to state whether that answer is greater than 1, less than 1, or pointless equal to 1. It's greater than 1. After I write that, I can say it diverges by the ratio test. And that's done. So that's a little bit of a step-by-step guide of what you are doing while you are using that. And yes, question.
So I don't know if it's just me, but I remember like when I first did the problem, I got 5/8 because I was kind of confused on where to leave the leftover.
Mm-hmm.
So like, how do I help myself remember like where to leave like the leftover after you like cross things out?
By leftovers, I'm guessing you're talking about what's highlighted here.
Yes.
Okay, let me grab that and move it because I've got too much stuff. Oh, no, that's not what I wanted to do. You know what? I'll erase. One thing you can do is focus on exponent rules, but you can also think logically about it as well, which is, I think, what you might be asking about. So I'm going to rewrite the yellow highlight, but I'm going to write it where I can see really nicely that this is 3n plus 4. And in the denominator, I have 3n plus 1. With that bit by itself, get this out of the way. What you can do is see that 3n plus 4 is 3 more than the 3n plus 1. If you want to look at it that way, you have 3n plus 1 times an extra -2 and 3 of them multiplying. Is that what you were looking at? And then, okay. Mm-hmm. And then we're ready then to take a look at number 4. Okay. So I want to also talk about number 4 because it has a factorial in it, and I want to make sure you're clear on how to deal with that factorial. Actually, I'm going to get rid of this. Give me another bit of room. Okay. When I begin the ratio test, limit as n approaches infinity, absolute value, and I replace each n with an n plus 1. But we are looking at parentheses n plus 1. N plus 1 minus 2, I'm just going to write n minus 1. And then that's the n plus 1th term. I'm dividing it by the nth term by multiplying by the reciprocal. And I want to look at this exponent is 4n plus 4. And I'll do this a little bit at a time. I'll start with the e to the powers. With the e to the powers, you should see that there are 4 more e's in the numerator multiplying than there are in the denominator multiplying. Now, when it comes to the factorials, there's a lot that is going to cancel there. I realize that you might be a little bit unsure as to where to start with the factorials. I'm going to erase this part right now so that I can show a little bit more here. Anytime you have something factorial, that is the same thing as writing that something and then, let me see how I should put this. I don't really want to just put an X, but maybe I should. Whatever you have that is in the factorial, that's the same thing as that times whatever that is minus 1 factorial. Or it is whatever that is times it minus 1 times it minus 2 factorial. So you can keep going until you reach what is necessary with the factorial to cancel with another side of the fraction. But I realize that you may look at this and not know which factorial to play with. So what I'll do is I'll start the way that isn't going to work. Let's say you take the n minus 2 factorial and just kind of see, 2 bigger, start there. You get what I'm saying? It happens. So you go, all right, n minus 2 times, and now I need to subtract 1 from that expression. And then I need to subtract 1 from that expression. And wherever you stop, you put a factorial. But then you look at the bottom and go, well, that's not helpful, is it? So what you do is you pull out your eraser and go, start again, realizing that this is the one that needs to be expanded. So this is now n minus 1 times, and then subtract 1, and you've got n minus 2. And right there, if you stop it by putting a factorial, you have what you need to cancel, and you can see what is left. Now, if that numerator had been an n minus 3, so different problem, I'm just saying, let's even say you had this. N minus 1 factorial is n minus 1 times n minus 2 times n minus 3 times n minus 4. And if I decide that that's far enough, I can throw the factorial on the very last one that I wrote. And then these cancel, and I'm left with 1 over that third degree polynomial. So now back to this particular limit. Once I cancel the factorials that I'm able to, I'm left with e to the power of 4 divided by n minus 1. And I'm solving the limit where n approaches infinity. And if you take a good look at it, you can see the answer to this limit is 0. And we are finishing up the ratio test. So you want to remember what you were doing with this limit. The purpose of the limit was ratio test. So your concern is less than 1, greater than 1. It is less than 1. And then at that point, you have a response. You converge by ratio test. And then that problem is done. Now, I want to show you what I posted. I just have to find it. There it is. I posted this earlier today, and I want you to be aware of what it is and what we have not done yet. And also, I took this from a previous textbook that I've used and just redid it with just the essentials, but it's primarily something that I've seen in another textbook. So you've got a column for what causes it to converge, another column for what causes it to diverge, and then a column for what makes it inconclusive when you cannot actually use that test. Now, so far you have these top 3. The test for divergence, or nth term test for divergence. You can't conclude converges. You can only conclude diverges if the formula for the actual terms is not heading to 0 or just does not exist. If you are getting 0, you are inconclusive. This is the person at the door of Club Converge. They say, go ahead into the lobby where an array of tests is waiting to determine if you're good enough to converge. You also have the geometric series test. This has to be, though, a pure geometric series. We're going to understand a little bit more later what I mean by pure. But it has to have a formula where it is specifically multiplying by one number to get to each next term. And you have converges if the absolute value of that r is less than 1. You have a diverge if the absolute value is greater than or equal to 1. I want to take a moment to point out that the ratio test we just learned uses an inequality with 1, but it's a reverse situation. Or not reverse, sorry, it is, sorry, I'm ahead of the game. Today we're learning P-series and then we'll explain. But the same inequality holds with the ratio test at the bottom. Looking at the limit as n approaches infinity of the absolute value. If it's less than 1, converge, greater than 1, diverge, but equal to 1 is inconclusive, which means you can't even use the ratio test. Everything you just did to get to this conclusion was a waste of time. So you've got that bottom one and these top 3 ones. And after today, you're going to have the next 2 underneath this. And here we go. In section 11.3, we learned the integral test. This is the integral test. If you are dealing with a multiple choice type of problem, you might be able to just quickly look at your formula, think about its integration, and go, I know the answer, and just answer it. But a multiple choice problem could also ask you some detailed questions where you have to know a lot of the specifics that go on in the integral test. Also, if this shows up in free response, which it has done in the past, you have to know the details. So I want to mention first that they're using f of x and a sub n. And what they're basically telling you is these are the same formulas. It's just when we use integrals, we usually are working with the variable x. When we are using series, we're usually using the variable of sigma as n. It's just replacing the n's with x's and throwing it in an integral and adding a dx on the end. And with improper integrals, you may remember that you can get a converge or a diverge with those. And the converge diverge depends on looking at a limit based on the infinity that it's heading to. If that limit exists, converge. If that limit does not exist, diverge. And I'm going to make sure that you get the idea as to why it is that if you put this formula into an improper integral from 1 to infinity, or actually from any constant to infinity, that if it converges, so does sigma. But if it diverges, so does sigma. Before I show you the picture associated with that, I want to emphasize that there are conditions. You need to be aware of them. When you rewrite this formula as f of x, do understand that you're changing the domain. In sigma, the domain is just positive integers, just 1, 2, 3, 4, 5, 6, 7. You get a bunch of dots if you're drawing a graph. But when I turn it into a function inside of an integral, I'm now looking at a continuous version of that same formula. So that function has to be able to be continuous. It doesn't necessarily have to be continuous from 1 to infinity, but it has to be continuous from some starting number to infinity. The other thing it has to be is positive. We need it to be above the x-axis. Because when I combine that with decreasing and being continuous, I will end up with a graph like this. That is asymptoting towards 0. And what I'm going to do is I'm going to give you pieces of the proof. Your textbook goes through full proof of this test, but I want to talk to you about really essentially what it's doing. So I'm going to block this off. This figure is going with all this. This figure is going with all that. And before I go there, though, I want to point something out to you. If my only concern is converge or diverge, taking one real number out of the sum will have 0 effect on just does it converge or diverge. It does change the sum, but it doesn't change the question on does it converge or diverge. So what this allows us to do is to choose whether we want to look at sigma starting with a, quote, first term versus starting with the next term out. That I'm getting the same answer of converge versus diverge. Is that last question still a question?
I was asking if the statements were like said above would be converse.
Ha 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 ha. Remember that I told you about that if and only if? So that right there tells you that it goes both ways. And thank you. That is a very important question. So what I want you to do is look at this. If I graph the sigma right here, starting at n equals 2, then for n equals 2, I'm going to plot this point. This is my a sub 2 value. Then when n is equal to 3, I plot this point, and that is my a sub 3 value, and so on. The beautiful thing is, if I'm going by integers, that creates a width of 1. And if I'm looking at an area of these individual rectangles, then a width of 1 multiplied by the value of the third term is the same number as the value of the third term. And I can look at the area of this rectangle as being the same quantity as my third term. This is the same quantity as my second term, my fourth term, fifth term, and so on. The figure 6 underneath it is bringing in additionally the first term, whereas the previous one started with the second term. And the thing that's beautiful is that allows me to set up 2 inequalities, 2 very important inequalities. If I am looking at figure 6, when I add all of these terms together, beginning with the first term, I have more area, which is equal to that sum, than I do have area underneath the curve. And as I head to infinity, I wind up getting this inequality, And that inequality is useful if I'm dealing with something that is divergent, because if this improper integral is divergent, that's because it's infinitely big. And if my sum can be shown to be larger than infinitely big, it also must be infinite. So this picture is useful in the case where you're getting divergent. The picture isn't changing from figure 5 to figure 6. The only thing that's changing is whether I'm dealing with my integration being convergent or divergent. I could write both of these inequality statements. They are both true. However, they are only useful to me. This one is only useful to me if I'm dealing with convergent. This is only useful to me if I'm dealing with divergent. What I want to do is I want to show you why the integral test works without going all the way into the proof. And what I want you to know is anytime you have sigma, you can actually write it both of these ways. The thing is, if you are dealing with the integral from 1 to infinity, if you're dealing with that integral as divergent and it's heading to infinity, this inequality isn't quite helpful. This inequality says, hey, you know what? You're smaller than infinity. And it's like, well, yeah, but am I finite? Or am I just a smaller infinity? Whereas this one, you can see clearly that if I am greater than something that is infinite, I'm infinite, no doubt. So either inequality goes all the time. It's just the one we are looking at for the individual issue of convergent, divergent changes out of usefulness. It's not that you're getting a different inequality. It's just which one is going to actually get me to a conclusion. If I have a convergent, this will not help me. If I have a divergent, this will not help me. So then let me emphasize, because I just talked about it being divergent. If your sigma, or not your sigma, if your integral is convergent, then it is finite. And the fact that we were dealing with a function of positive numbers only adds a border over here as well, which is necessary. So what I'm looking at is if this converges, then it is finite. If my infinite sum is between 0 and a finite number, it has to be finite. In this inequality, if I look at my convergent real number and I realize that my infinite sum is larger than a real number, well, how much larger? Is it infinitely larger, or is it just a bigger finite number? It's not enough information. So at all times, both of these inequalities are true. It's just they are only useful under the different circumstances. And that's what allows me to just make this big, blatant general statement of if my integral, my improper integral converges, so does sigma. If my improper integral diverges, so does sigma. They just both do the same thing. And that's what all of this is saying. Now, I'm going to go through an example, and I'm probably only going to make it through one example, And I may continue after class is over and go through some more examples if you need that. We're going to use the integral test to determine convergence divergence. So that means that I'm going to rewrite this formula with an x. Do I have to rewrite it with an x? No. But whatever variable I use, that's got to be the variable of my integral. Now, do I have to start at 1? No, I don't have to. But I need for whatever number I do start with to infinity, I need for this function to be continuous, positive, and decreasing. So if I'm going from 1 to infinity, do you see that this is continuous if I allow it the domain of real numbers? It's only going to give positive numbers for its output. And if I'm going 1 to infinity, it is definitely decreasing. So consider those check boxes. If those are true, then you can turn to the question of, does this improper integral converge or diverge? So we've got to go back to a long time ago and write that this needs to be turned into a limit. I'll use the letter B for the upper limit. And do you recognize that integrand? That integrand is directly a derivative formula. Who is this the derivative of? You got it, arctangent. Now, right now I'm writing more steps than you necessarily have to sit here and write because it is a bit tiresome. But as I go through an example, I want to make sure to not skip things that I'm writing. Finally, I'm going to write the limit that needs to be solved. I need to solve this limit. And it comes back to, do we remember what arctangent looks like? It's tangent reflected over the line y equals x. And it has asymptotes pi over 2 and negative pi over 2. So if I'm trying to answer what is the limit as the input heads to infinity, I get that it's heading to pi over 2. Minus, and then the arctangent of 1 is looking at what angle causes tangent to give you 1. Tangent is the same thing as slope. So what angle makes a slope of 1 within arctangent's domain? And that would be pi over 4. Yep. Now, do I need the pi over 4 answer? No. I don't need it. All I needed was to come to the conclusion that this limit exists. Because the limit exists, the improper integral converges. What? Keep it there. Because this limit exists, the improper integral converges. And because the improper integral converges, sigma converges by the integral test. So that's the step-by-step process. You guys. So the answer to is this series convergent or divergent is it is convergent. The test used is the integral test, but this is the entire process needed to properly do the integral test. Now, I've got some good news for you. The integral test is what I call the it is the last resort. Pretty much anything is better than the integral test if you see it. It is, again, a last resort. If you look at some of the problems in this section, the ratio test is going to take so many of them and just done, flatten them quickly. Whereas with the integral test, it's a little more cumbersome. So know that your go-tos at this point are, if you notice you have a harmonic series, just throw that down. If you have a nice geometric series, use it. And I'll talk more. It's geometric when n only exists in the exponent. Don't forget about the divergence test. So you've got those three. Before heading to an integral test, I would go through some of these other ones, but you don't have them yet. But I would consider ratio test before I turn to that integral test. And what I want to next show you is a little bit of what you're going to see on the homework. And then I have some more to go over with you. Okay, so some of the homework problems are going to ask you to determine whether the series is convergent or divergent. And this does not tell you what test you have to use. I'm going to talk about the problems I've circled later, but I'm going to first go over to these. I chose these three for the integral test because if you look at each of these three in the ratio test, they're going to give you a result of 1, which means the ratio test is inconclusive and can't help you. I will say that a lot of times there is a way around the integral test, and people have their preferences at that point. But if the ratio test is not going to take it, the integral test is becoming one of your better options. And so you're going to be solving those with the integral test. And the reason I have 3 of them is because I realize you need to practice your integration skills. Could you technically make the first limit of the integral? Yes. You can make the first number of the integral be anything starting with whatever their starting number is or more. And then for 21, no. Just because it's multiplying by a harmonic doesn't mean divergent. Because I've got an infinite, basically it's kind of an infinite series multiplied by a harmonic. It's not a constant times a harmonic. Yes, if they were adding, divergent, done. But multiplying, different game. And we do have more tests coming that are going to help us see some other options we might be able to use for these. But at the same time, they are options where you have to realize that that's an option and it's not obvious. So, Okay, so the way that I look at a quick way of determining that the ratio test is going to end up being 1. If you think about plugging in an n plus 1, and just take a moment to think about that, can you see that as a ratio, that's heading to 1? A logarithm, I'm heading to infinity. So it's the natural log of 300 divided by the natural log of 299. And more. And not quite. It's more an issue of if you look at large numbers, let's say the natural log of okay, if I compare those, my calculator might actually tell me 1 because it's so close. When I'm dealing with polynomials and I'm circling things that are polynomials, the ratio test is going to turn into the number 1 with those. No. You're thinking of your log rules incorrectly, and it's really normal to do that. The addition, so if I have natural log of n plus natural log of 1, that is not the natural log of n plus 1. It is the natural log of n times 1. Addition inside a logarithm can't be split. So the ones where the ratio test would be super nice. Which ones did I not do? That one, ratio test, is just going to suck it up. Gulp. I'm going to, for some of them, there were other reasons I laid off of them. If you have something like this where you are dealing with only polynomial involved, this is a polynomial and a logarithm. This is a polynomial and a logarithm. This is a polynomial and an exponential. That multiplication makes this a little extra difficult. But if you saw this at the end of this unit, you would not use the integral test for it. You wouldn't even think about the integral test. And you'll see why when we get there. There is not a single test that's always the best one to go. And there are patterns that lead you to a particular test, but it's not always going to work. I will tell you this. Anytime factorial shows up, go directly to the ratio test. Do not pass go. If you get the joke on that. For those of you Monopoly players. I grew up with Monopoly, but it got put away for a few years because of arguments. Anyway, moving on. I need to teach you one other test, and it's very, very important. Yeah. Okay. Focus, math. We're going to come up with a test that is a byproduct of the integral test, and it is called the P-series test. The P-series test is dealing with this situation. And to best help you see it, I'm going to do the following. I'm going to do an example where P is 1/2, a quick example where P is 1, and an example where P is 2. I just realized something I wrote wrong. There we go, n to the 1/2 power, or otherwise known as the square root of n. Okay, here we go. Now, do you recognize this? This is harmonic. It diverges. With the integral test, we can actually use the integral test to show it diverges as well. And I'm going to mention that very quickly. If I integrate from 1 to infinity 1 over x dx, I am getting the natural log of x basically from 1 to infinity. And that heads to infinity. Slowly, but it does. So by the integral test, you can show that the harmonic series diverges in another way. Now, I had to put this one up because you cannot use the power rule in integration for this one, but you can for everybody else. So when I rewrite the other two, actually, let me do this. If I rewrite 1 over x to the 1/2 power as x to the negative 1/2 power, then it's the integral who either converges together or diverges together with sigma. Over here, I'm looking at the integral from 1 to infinity of, instead of writing 1 over x squared, I will write x to the negative 2. Need some space. Okay. So I'm going to try and do this relatively quickly. When I integrate, I add 1 to the exponent. That's going to make 1/2. And then I divide by that exponent. So ultimately, I get 2 root x, and realize that I'm evaluating that from 1 to b as b approaches infinity. Do you see that this is very diverging? When you look at this one, you add 1 to negative 2, and that brings you up to negative 1. Divide by that new exponent. So I'm getting negative 1 over x evaluated from 1 to some b with the limit of b approaching infinity. Does that limit exist? This limit exists. The only thing that matters here is, does the limit exist? Realize the answer to the improper integral will not be the same as the sum. You can use it as an approximation, but the answer to full area under a curve is different. Yeah. I'm just not going to write the answer because that's actually not the point. The point is, does the limit exist or not? This is a does not exist limit. This is an exists limit. And that is all the difference between diverge and converge. And now I want you to see the two sides of one. This is p equaling 1. This is a representative of the p's greater than 1. If the p is greater than 1, when I integrate, I will wind up with a positive exponent on my variable in a denominator. When my p is smaller than 1, when I add 1 to that exponent in its negative form, I will end up with a positive exponent, which means my variable with a positive exponent is in the numerator. And putting infinity in a numerator versus a denominator is the difference between converge and diverge. So that gives me the P-series test. And this is it. And it's nice and simple. The P-series test is, all you have to do is look at it and go, this is P. So for example, if this was 1 over n to the 5th power, then you would say P is 5. 5 is greater than 1. Converge by P-series. Done. If the P had been, say, 1/3, then you would say, oh, my P is 1/3. And you know what? 1/3 is less than 1. So therefore, it diverges by P-series. And that's it. You're done. P-series is really, really nice. Now, on your homework, I'm only giving you 5 problems. And I want you to know that these first 2, I want you to use P-series test on. And those bottom 3 that I showed you before, these, you don't have enough tools to go around the integral test yet. And you might even want to use the integral test even with those tools. Right. This is a rule for an entire series, an entire type of series. This allows you to not have to throw down the integral test with a particular formula that shows up over and over and over again. And so what you have now is you have the test for divergence, geometric series test, a harmonic series that you could actually say it diverges for many other reasons. You have the integral test, which is your last resort. You also have P-series test, but this is where I want you to look very carefully at the P inequalities for converge diverge versus the R inequalities for converge diverge. If you don't understand why the geometric series test converges diverges the way it does, and you don't understand why the P-series test converges diverges by the way it is, you are going to mix those up. Even if you know them, you're still going to have that accidental, silly mistake. But if you understand why a geometric series needs to have its absolute value of r less than 1 to converge, and why with a P-series you need the exponent on that denominator to be bigger than 1 if you're going to converge. If you understand why, you're going to mix it up far less. When I think of P-series, I actually picture the integral test. I take a moment to think about the integral test with P-series because that allows me to think about the issue of adding 1 to the exponent and whether that causes a negative exponent to become a positive versus it's still negative even if you add 1, it's so negative. Versus with the geometric series test, I try to always picture an older idea in my head of if I multiply something by a number less than 1, I chop it up into little pieces, which is something that's in a more distant memory in my head, which probably is for you too. Whereas if I multiply by a number bigger than 1, hello, means growing crazy. So find those resources in your head that you already have. You understand the geometric series, but you need to grab onto those things that you do understand about multiplication. With P-series, you're going to grab onto the more recent understanding of the power rule when you integrate. and the issue of adding 1 to a negative number. If that negative number is larger than 1, it's still going to be negative after you add 1. So you've got those, and then we don't have very many tests left. After that, we only have 3. And you already have the ratio test. There are technically there's a little bit more to these in a calculus textbook. For the AP test, there's some that they decided not to bother with. And I can talk to you about those, but these are the ones you need to know. And I'm over time again. Huh. Who knew that would happen again? So I'm going to stop my video.